In this lesson, we will learn about the probability density function, or PDF for short. Now, as a quick recap, in the previous lesson, we learned that by looking at the shape of our histogram, we can derive some general properties of our data distribution. However, we also learned that the shape of the histogram heavily depends on a choice that we made, namely the bin size, or equivalently, the number of bins in our histogram. And therefore, we are now looking for something that also allows us to derive some general properties by some visual inspection, but whose shape does not depend on any choice that we made. And this brings us to the probability density function. Now, instead of starting out by giving you the definition of the PDF, I think it is better to start with the histogram and see how we can transform it into the probability density function. Now, to do this, we have to imagine what happens to the shape of our histogram if we increase the number of bins indefinitely. Now, fortunately, you don't have to imagine that because I've made an animation that does just this. In this animation, we will go through the transformation from histogram to PDF step by step, by at each step along the way doubling the amount of bins in our histogram. Now, note that doubling the amount of bins means cutting in half the data interval for each bin, and this will be important later on. We start out with a histogram with 15 bins, and at each step we will double the amount of bins. Now also note that at each doubling step, these numbers here on the left hand side on the y-axis, they halve, and it is a good exercise for you to try and figure out why this is, just to test your understanding of the histogram. Now, if we keep doubling the amount of bins, we see that at each step, the shape of our histogram smoothens out. And we can imagine that at some point, we can trace the shape of our histogram by a continuous curve. And it will be this continuous curve that will be our probability density function. Now, what do we actually gain by going from the histogram to the probability density function? And before we talk about our gains, we need to face our losses. Namely, that the probability density function is an approximation of our histogram and thus of our underlying data. Now, why would this be? Well, to understand, we need to think about how we obtained the probability density function. We started from a histogram and we increased the number of bins indefinitely. Now, remember that increasing the number of bins means decreasing the bin size of each bin. And at some point, this doesn't make sense anymore. Think back about the example of the previous lesson, where each data point was a person's height with a precision of 1 centimeter. Therefore, if we increase the number of bins, at some point the bin size will become smaller than 1 centimeter, and at this point the procedure will break down. Therefore, we can conclude that we can view the probability density function as a limiting case of a procedure that we just cannot do for real-life data. Now, what do we then gain from this procedure? Well, first of all, the probability density function is a function, a mathematical object which is described by a mathematical formula. Now, why is this beneficial to us? Well, because a mathematical formula allows us to compute interesting statistics of our data distribution. For instance, the average or the variance, the broadness of our distribution. Now, this wasn't possible by just looking at the shape of our histogram. There, we could only get some qualitative insights in our data. And of course, another gain that we get is what we set out to look for, namely something that, by visual inspection, allows us to get some insights into our data distribution, but crucially, whose shape does not depend on any choice that we made. In fact, the shape of the probability density function is only dependent on the underlying data. And it goes even further than that. The shape of the probability density function is only dependent on the data generating process. Now, what does this mean? It means that, for instance, you could have a various different sorts of data sources, each with their own data distribution. However, all of these data distributions are described by the same type of probability density function. Now, we will get into much more detail in later chapters, but just to give you an example. Whether you're looking at the income distribution within a society, the population size of cities within a country, or even the magnitude of earthquakes within a continent, all of these distributions are described by the same type of probability density function. Now you are probably aware that there is one probability density function that is ubiquitous, that comes up time and time again. And in fact, it's the one that is right here, with this bell-shaped curve. And therefore, it is worthwhile to spend the last few minutes of this lesson digging into some details of this distribution. This bell-shaped symmetric probability distribution is called the normal distribution, and it is represented by this mathematical formula right here. Now you don't need to learn this formula by heart or even exactly understand what each symbol means. Just remember that as a function, it takes in an input, x, and as output, it gives another number. Now in this case, this output number is proportional to the probability of finding the input number as a data point. Now we are of course interested in the shape of the distribution which this formula represents. And in fact, for the normal distribution, there are two numbers or parameters that change the shape of the distribution. The first one is the average or the mean, represented by this Greek letter mu, which comes back in the numerator of our exponent. And now to see how this parameter changes the shape of our distribution, I made an animation where I draw a normal distribution and only change this parameter, this mu representing the average. So let's see. So I draw this normal distribution and observe that changing mu only shifts the entire distribution over the x-axis. And this makes sense if we remind ourselves that this distribution represents the underlying data or is an approximation for its histogram. Thereby, if we change the average, this means that we just shift the entire data along the axis. The other parameter that determines the shape of our normal distribution is the spread or the variance of our distribution. It is represented by the Greek letter sigma and can be found in the denominator of our exponent. Also here, to visualize what sigma does to the shape of our distribution, I made an animation where I draw a normal distribution, but this time I only changed the value of sigma. And we see that it indeed represents the spread or broadness of our distribution. If sigma increases, our distribution spread increases, it becomes more broad. If sigma decreases, it becomes a more peaked distribution. And this is how the shape of a normal distribution is determined by just two parameters. And in fact, all of the other probability density functions have their own parameters that determine their effective shape. And this concludes our chapter on the histogram and the probability density function. Now in all subsequent chapters, we will learn how to implement these ideas and many more concepts with using Python code. In fact, in the next chapter, we will learn how we can generate our own dataset and make a histogram of it. So let's get coding.